In section 4.6, we're going to look at a special triangle congruency called the hypotenuse leg theorem. So this is similar to when we were using side, 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 angle, angle, and angle, angle, side. We're going to add then hypotenuse leg. Now remember, we're not allowed to use side, side, angle. And what hypotenuse leg is, it's looking at a special case where because we have a right angle, this actually works. But we're not going to ever call it SSA. We're never going to use that, but we can use hypotenuse leg. So if we look at what's happening with a side-side angle theorem, we're looking at an angle, and then the sides. Okay, notice that our sides are the same. I've got four the same, so my side, another side, and then an angle. But notice here, even though I have the same angle here and the same sides, these could go different ways. Basically, this 4 over here could be drawn coming back here, so I could have this isosceles triangle here, and we're not sure which way we're supposed to go. So we can never use side-side angle. But look what happens when we make it a right angle. If I look at this triangle here, we see that, okay, here's my side that's congruent is this green side. We also have this bottom side, and then we're copying this angle over here. So again, notice as I change the length of the side, there's two ways that I could go to have that same side length. So my angle is the same, my side is the same, but it gives me two different triangles, this yellow one and the orange one below. Notice the yellow one's overlapping, so it's the whole thing there. Now look what happens if I move this out a bit. If I make this approximate a 90-degree angle, and I make this big enough to see that, notice I no longer have two lines. So we're allowed to use hypotenuse leg because we have this right angle. Now a little vocabulary, hypotenuse, remember, is across from the right angle. The other sides will be the legs of your right triangle. So with our hypotenuse leg theorem, we'll be looking at the angles here. So we must have a right angle. We look at the hypotenuse, and they are the same. And then we have one pair of legs that are the same. Now these things could be turned in different directions, but as long as we have a pair of legs the same and the hypotenuse the same, and it's a hypotenuse because we have a right angle, then those triangles will be congruent. The proof of this is a little bit complicated. We're looking at two right triangles here, and they're defining which ones are the right angles. Our first step, we're going to need to make this a little bit longer. They just say extend this side over here. So basically what they do in this first step is make this line keep going. Now notice that's going to give us another right angle here. This is just a skeleton of the actual proof. We won't put everything there. Now the next step is they say mark point S so that this side here is actually congruent to RQ. So that's what we're marking here. We want S to be congruent to that. So we can construct that like we did with our compass and straight edge. And then we notice again, these two angles have to be, each are right, so those are congruent there. And so if I extended the other side here, from X to S, if I connect that, these two triangles, the one I copied QR from, would have to be congruent to XYS because of side, angle, side, side, angle, side. Now notice I don't have this side yet, so we haven't proven these two yet, which is really what we're after. All that we have right now are the one that we just created and the PQR. Now the next steps of our proof, then we start to compare the corresponding parts there. If I do know that PR, I constructed it to be congruent here. Because I know that PQR and XYS are now congruent triangles, I know that their parts match up, so I can match this as being congruent. We should notice then that X to Z, this is given that PR and XZ are the same, so I can make, using the transitive property, I can show that XS over here is congruent to XZ over here. Our next step then, we look at the base angles here. Now notice right now we still just have two sides and angle here, but now we're getting another angle here. Because we can say that these two are congruent because I now have an isosceles triangle. So they're saying S is congruent to Z because it's isosceles triangle theorem, We can now note that this triangle XYS, the one that we created, is congruent to XYZ by angle, angle, side. And then that will also give us, with the original one, since these two are congruent and these two are congruent, we can kind of loop back around and get PQR congruent to XYZ. So the congruence of triangles is also transitive. Okay, in this proof, we're going to prove that these two triangles are congruent. Now let's look at the information that's given to us. First of all, we see that these two sides that are marked as congruent, and that we have a perpendicular bisector here. Now there's a couple pieces of information we can get from this being a perpendicular bisector. One of the things being perpendicular, that would tell us that angle CBD is a right angle, as well as angle EBA. It would also tell us, since it's a bisector, that it's cutting this segment in half so that CB is congruent to EB. Again, this is all taking our definition of a perpendicular bisector. We get all that information from that. In our next step, we should notice, okay, now since I've got that already marked as right angles, I know that I have two right triangles here. If I look at those, I have a hypotenuse in each of those, and I have a leg in each of those that are congruent. And so I can use the hypotenuse leg theorem here to show that these two triangles are congruent. So the top one is CBD. And I want to double check my C corresponded to E, my B corresponded to B, and my D went with A. And that is what they asked us to prove, and so we've proven this.